Hello, and here we are, the big connection that ties everything together of calculus, where at this point, now we know what makes calculus calculus, and we're just going to be looking at applications of it moving forward. But here it is, the fundamental theorem of calculus, otherwise known as the FTC. And there's two parts to it, part one and part two, that I'm going to explain and go into a little bit more depth so you understand it. All right. Now, part one, straight from the book, is saying if you have a function that's continuous on the closed interval a to b, which I know you can't be continuous on the bounds here, but there's a technicality where f is continuous on a closed interval a to b, where it's called like left closed and right closed, something like that. But anyway, if f is continuous on an interval a to b, and the antiderivative of x is equal to the area under the curve from a to x of a function f of t dt, then if you take the derivative of the antiderivative, well, you'll get f of x for all x in that interval a to b. And all of this that is written in words can be summed up, is the same thing as this written here in math language, where the derivative of the area under the curve from f of t dt from some constant to a variable x will just equal the function at x. All right. So what's this mean? And I'll use a different color to debrief this. So part one, explained. So what this part of the fundamental theorem of calculus is saying is, say you have a function f of t that's continuous. All right, so you have a continuous function f of t. And if you watch my last video, there's a reason we use f of t and not f of x. And that's because when we say a bound to a random variable x, we don't want to confuse the x's. So they just use a function f of t, just not to confuse ourselves. So say we have a function that's continuous. And if we want to evaluate the area under the curve of f of t, so then we can look at some constant a, where a is just any real number, to some value, who knows what it is, of f of t dt. Well, remember that to get the area under a curve of a function f of t dt, well, you end up getting an antiderivative of that function, and it's in terms of x. And it's in terms of x because if you picture, a graph of this, and I don't know f of t looks like, arbitrary value f of t from a to x, well, since x is changing, right, the area is going to change depending on how x is. So it's an antiderivative in terms of x. So that's not new yet. That's not the fundamental theorem of calculus. That's just saying we have a function that's continuous. You evaluate the area under the curve of f of d dt from some value to x, any real value. Well, remember that that's the same as the antiderivative in terms of x. Well, what this says, though, is that if we take the derivative of this side, so if we take the derivative of the antiderivative in terms of x, what you get, so I'll write down here, the derivative of the antiderivative of x is just f of x. So you get the original function, but just in terms of x, because that's where we're evaluating it. And really what that's saying is that the derivative of an antiderivative takes us back to where we were. So in a way, in a nutshell, it's just telling us that derivatives and integrals are inverses of each other. Just like addition and subtraction, multiplication, division, powers and roots, just like those are inverses of each other, derivatives and integrals are inverses of each other. We can work from one to the other, right? If we want to find the area under the curve, which is an antiderivative, well, by taking the derivative, we just get back to the original function. And that's very powerful because now it's a two-way street. Given one, we can get the other one and work bacheck to check our answer. All right. Now, someone is probably wondering, and maybe I messed up in my earlier video, how come when we take the antiderivative of f of t dt, which is a function f in terms of x, how come there's no plus c? Because you told us, Mr. Hein, that antiderivatives always have a plus c, and that's true. But the antiderivative that's being used here is not the same as a general antiderivative. This antiderivative is unique in the sense that it's relating to this function here, but the reason there's no plus c is because this antiderivative relates to this problem, which is area under the curve. A plus c, a vertical shift, or an extra value, it doesn't make sense for area under the curve. Right. Where it comes into play, side note, before I get into the second part of this, is in what's called indefinite integrals. And an indefinite integral, unlike what you see in this, which means no bounds on it, no bounds. So if you just have an integral of f of t dt, so if you just want to find the antiderivative of a function, you're not talking about area under the curve, there's no context here. Well, yeah, there's infinitely many antiderivatives, so you would put plus c. But this meaning of antiderivative, when we talk about no bounds, is very different than when there's bounds, because bounds is now referring to an area under the curve. Okay. So part one, in a nutshell, is telling us the derivatives and integrals are inverses of each other. You can take the derivative of an antiderivative and get back to its function. All right. An example of this, very quickly, is say you want to find d dx of a to the x, and notice a can be any number. So let's say I actually put a number in here. Why not? Let's say I put in the number 60 to x of, say, t plus 1 dt. Well, what that's saying, what part one is saying is that, well, t plus 1, that curve, is going to have an antiderivative. So it's going to have some antiderivative, f of t, right? But when we evaluate it from 60 to x, well, then that becomes, we're evaluating it in terms of x, so it's really f of x, not f of t. And then when we take the derivative of f of x, well, we just go back to f of x. So the answer here is you could just actually write x plus 1. And there is, a pretty easy way to see these where the derivative of this integral is you just take x and substitute it for wherever the values t are. Because that's really what's happening. The lower bound doesn't matter here. Okay? Because we're not trying to evaluate it, we're just saying that an antiderivative exists in terms of x. Okay? So that's part one. Part two. If f is any function such that, if f, the antiderivative, is any function such that the derivative of the antiderivative exists for all x in the open interval containing ab. All right, so you have an antiderivative, and the derivative of the antiderivative, which again would just be like f, exists. Well, then, to calculate a definite integral, because again it's bounded a to b, we can just take the antiderivative and look at it at its upper bound and its lower bound. So what part two is really telling us, part two explained, is really just telling us how to use the fact that antiderivatives and derivatives are inverses of each other. And we use this to actually calculate definite integrals. Definite, which is just another word for bounded integrals. Okay. So if I give you an example of this, say I said, let's find the integral of 1 to 3 of t dt. So what's the area under the curve of a curve t? Well, what we can do is just take the antiderivative of t, which is t squared over 2, where you add 1 and divide by that. And you just look at it from its lower bound to its upper bound. where we say t, well, then we plug in the upper bound, 3 squared minus 2 minus 1 squared over 2, right? Where that, picture this, so if that was f of t, picture this being the antiderivative, f of t, so this is f of 3 minus f of 1, which is what it's telling us in the derivative. And we can calculate this, which if you do the math here, you get 9 over 2 minus 1 over 2, which is 8 over 2, so that just gives us 4. Okay. Now, from a graphical perspective, because I know it's sometimes nice to see what these look like graphically, so you have the original curve was t, and we were looking at it from 1 to 3, and I asked you what's the area under that curve, the exact area. Well, we found this by looking at its antiderivative, because part 1 is telling us that, well, there's an antiderivative that we can use that is related. So there's an antiderivative, t squared over 2. So this is the antiderivative, and this is the function. Well, with the antiderivative, if we just look at the value at 3 and subtract the value at 1, we actually get the area from 1 to 3. Now, the way you might see that, because you're like, that's very odd, Mr. Hein, is f of 3 is really the accumulation from 0 to 3 of the original function f of t. So it's kind of like the accumulation from 0 to 3, however much was adding on a distance or an amount. And f of 1 is the accumulation from 0 to 1 on f of t. So notice that when we see these as accumulations, if f of 3 is everything that's accumulated over 3 hours, f of 1 is everything that's accumulated over 1 hour. If we subtract these two, that's what gives us the accumulation or the area under the curve from 1 to 3. So there it is, the fundamental theorem of calculus explained. If you have any questions, if there's anything in here I probably left you on, I know you have to work through some yourself to understand it, but very, very big idea that part 1 is derivatives and integrals are inverse of each other. Part 2 is really how we use it to calculate definite intervals. All right. Hope that helps you. Bye-bye.